Welcome back. See, the number of people decreases a little bit. But we are just about to getting to the interesting part now.
Yeah.
So, okay, so without further ado, let's have Tung continue.
Thank you. Yeah, so I just wrote down. So first of all, I apologize for being a little bit back yesterday, especially during the last 30 minutes. I mean, I think if you try to work out the proof rigorously with careful calculations, and you can get the lemma about that describes the idea of adding an edge, adding a missing edge to the graph edge, and we try to gain the count of h or h plus e start post graph e. Then if something goes wrong, then we're going to get the redundant pair. And the nice thing about the argument, if you look at it closely, is that we have the freedom to actually choose the density between A and B. So this statement, I mean, this lemma holds for any density you want, and the trade-off is only a similar factor in the number of copies of relationship. So, I mean, for me, this is not especially difficult to carry out. I mean, as long as you get the idea. And also, I would like to remind you, the density result of Erdős and Hajnal for HB graph G, which led to the C loglog and bound that they got initially for the conjecture. So the goal today, we will try to convince you that
Please use yours like.
Yeah, so the goal for today, I'll try to convince you that we can really improve the general result of Erdős and Hajnal just a little bit, and I'll try to explain the reason behind the bound and how we can get closer, or actually get it completely using some key ideas. So, theorem by Matija Bucić, myself, Alex Scott, and Seymour. And the paper which is published, and this is for every edge, there's C, then for the depending on edge only, such that if G has M with C, and H free, then you can always find a clique or independent set in G size list GPC times root log n, similar to the additional bound, but now we have an extra double log n inside the square. So so this currently the state of the art bound for excluding any general graph edge. Okay. So now let me try to explain a little bit about how we can get this bound. Okay, so this looks pretty funny at first, right? Because there should be no reason why we have the double log term there, especially inside the square root. And yeah, but actually this bound was I think was not first recognized by the four of us. I think maybe 10 years ago, a group of researchers, David Cullen, Jacob Fox, and Benny Sudakov already recognized this. And what they observed was to improve this Erdős-Hajnal theorem for pairs, for very sparse or very dense pair in the HB graph. And what they wanted to improve was to improve the size of one of the two sets. So here, as you can see, bound here has polynomial form, right? I mean, it is a polynomial in epsilon times the number of vertices of G. And Colonel Fox and Sudakov make a conjecture. Is 15. It's still open. Every age. With the example hypothesis as in the Erdős-Hajnal theorem. Then there's a D positive such that every H3 graph G. And now you can find this joint. That again A is epsilon stars or epsilon bands. And here, of course, epsilon is on 0.5 as usual. Now, so instead of both A and B polynomial size, one of them is going to have linear size. So one of them, and the size of one of them is going to be independent of epsilon. So A is this G over D, and B is this epsilon B. Yeah, so the trick to get the I mean, yep, so this so if you forget about this double log thing, and if you only look at this very dense or very sparse pair result or conjecture, I mean, you'll see that, I mean, this conjecture is very natural. I mean, if you want to try to make a step up from the Erdős-Hajnal theorem, right? You want to try to get rid of the dependence of the dependence of the parameters on epsilon. And this actually what would give you this loglog bound, and the calculation is pretty messy, so I'm not going to explain in detail. But later I will go back into this conjecture and then try to give you a good intuition why this should imply this bound. Okay, and this conjecture is still open, and it is even open for the triangle. So the current state of the art is, as far as I remember, is Q for C5, I mean Q for the 5 cycle. But you know already that the C5 has the Erdős-Hajnal property. So in some sense, this for C5 is a nice result, but eventually it has no effect on the final Erdős-Hajnal result for C5. And it is still open for the triangle. I think quite a few people in the area have tried, but no progress so far. So yeah, so this is a way, I mean, to get this funny double log improvement. So, and in the proof, I mean, in our proof of this result, I mean, we are actually going to use the idea behind, I mean, this polynomial versus linear pair in order to gain something more, and then to get the improvement. Right. So, so the next idea behind the improvement is a way to, I mean, to construct a copy of H in any host graph G. So actually, from the structural point of view, it is not very easy to do so. I mean, and this, I mean, that already seems highly non-trivial if you look at a path on 100 vertices, for example. So what is a good way to view an induced path on 100 vertices in any given host graph? I mean, restricted to some condition. I mean, that's already a non-trivial question. But for general graph H, if you look at the proof of Rödl's theorem before the proof using the regularity lemma, then there's actually a step where we constructed a copy of H by using pairwise epsilon prime regular blobs, right? And then we try to construct a rainbow copy of H from the configuration. So another way, which is maybe a little bit, with much stronger condition to gain a copy of H in G is as follows. So now we forget about regularity or anything. And we let's say we have a collection of disjoint project subsets in G. And let me say the vertices H are U1, 2, H, where this small h is a number of vertices H. Okay, so and now I also have H blocks, A1, A2, and so on to AH. Okay. So now what I would like to to see from the from the edges or what's happening between every pair among these blobs is, let's say, if for every I and j in the index set, and I distinct from j first, we have the fact that AI is epsilon sparse. Anyway, j we can only if AI gj is not an H, and AI is epsilon dense. Anyway, j we can only if AI dj is necessary. We need an active H. If this is true for any pair of ij, then it is not hard to construct a rainbow copy of H from this configuration. And the way to do this is very simple. For every block AI, you only have to pick a uniformly random vertex from the block, and then with very high probability, with the H vertices, the 8 random vertices that you picked are going to form a copy of H in G. Okay. I mean, of course, here we are assuming epsilon to be sufficiently small. That's just a technicality. Right. That's another idea to construct a copy of H. Which is a bit, if you look at it, then this condition is a bit stronger than just usual regularity thing, but it's going to be useful. So far, we have discussed 2 ideas behind the improvement, and now it's going to be the third idea, which is perhaps the most important one. So now let's look back to this first lemma, right? So of course, as we discussed, this lemma is about trying to gain account of H in a graph G, right, by using the count of H plus E. Except, with some exception that we can have a very dense pair inside this graph. So as we talked, as we discussed in the first lecture, Erdős-Hajnal is about the local global property, right? It's a manifestation of the local global property. But if you look at this statement, then you see that this statement is a little bit too global, in the sense that here we only concern the count of H plus E and H in the whole post graph G, and we are not doing anything locally. So there's no local count in the whole graph. So there's only global count, and with some exception here. So in some sense, this is a little bit weak. The next thing about this lemma is how it implies the density of observable theorem. As I said, we start from H, we try to add an H. You try to add a missing H to H, and then we keep going until we get a complete graph. And now we say the complete graph has to be viral, and so on. Okay, but if you look at it, then the proof, the final proof, doesn't rely on any particular choice of the order of the missing edges of H, right? You can just order the missing edges arbitrarily, and then you start adding them one by one. And then you get a proof. So in some sense, I mean, this is also a loose point in this kind of argument. And then in the next step, we're going to try to improve. Okay, so let me write it down here. So improvement. The first one is local counting. Second one is more control on these images. I mean, just maybe not so clear, but I mean, this is just something like a rough idea about how we can proceed. Yeah. So local counting means, I mean, you try to look at only a portion of the graph G instead of the whole graph, right? I mean, if you look at the first two outcomes in the lemma, then there's nothing that says about what's going to happen inside only a local graph G, but it concerns the number of copies of H plus E and H in the whole graph G. So in some sense, that's like a waste, right? We're not really doing anything locally here. Okay. Right. So there's something to improve here. And so now going back to this picture. Yeah, so far we've been talking about trying to gain a copy of H, I mean trying to do something locally, trying to use this polynomial versus linear pair condition in order to gain something. So now, as I said, this condition is still open for triangles, right? For the triangle, it is still wide open, actually. And the density of theorem above says that, I mean, up to some condition, we can guarantee a dense pair. So now, let me try to do what we can do, I mean, to gain a good blow up of the triangle from a dense pair. Now you can see. So let's say in some scenario, some very good scenario, we already have a dense pair. But I mean, this is A and this is B. Okay. So these are very dense vector. I mean, up to some very, very small density parameter. And I would also like to assume that, I mean, from the density Poisson theorem, that both A and B have exactly, I mean, just about some power of epsilon times the number of vertices of G. So both A and B are roughly for the epsilon. Okay. So which means the rest of the row is still huge. I mean, there's still lots of vertices. Now again, now we want to use this condition to gain the loglog improvement. Okay, so it would be very nice, right, if for example 1/3 of the rest of the row is very sparse to A, right? So if there is a subset, let me say C, of size about 1/3 of G, that is very sparse to A. So for example, and every vertex you can see only sees a very small portion of A. Then we're good. We have got a very sparse pair, polynomial versus linear that we wanted, and that's going to be a good outcome. Right. And at the same time, if there is a subset B, also at least, I mean, this size, right, which is also very sparse to B, then we're good, right? So far, I mean, we haven't done much. Just like, I mean, starting from this condition, I mean, granted that it would give us the loglog improvement. Okay. So again, if this one in the rest in the rest, let me say epsilon sparse in A or epsilon sparse to B, then you read, right? Just the condition. Right. So yeah, so we may assume that this scenario cannot happen. So what is it going to imply? So both of so this condition doesn't happen means fewer than 1/3 of the vertices in the rest of the world is are epsilon sparse to A, and at the same time fewer than 1/3 of the number of vertices in the rest of the world are epsilon sparse to B. And what this means is there's going to be a very large number of vertices in the rest of the world with a decent number of neighbors in each of A and B, right? So this A, this B, so at least 1/3 this is G, for example, or maybe G minus something versus each at least epsilon A neighbors in A, or at least epsilon B neighbors in B. Actually, not all but M, at least epsilon. So each of them is going to see a very good number, a pretty good number of people inside each of A and B.
So can you say again why if at least 1/3 epsilon sparse to A or B will win again?
Because of this condition, polynomial versus linear. Oh, so it's not like,
Okay.
yeah.
Mhm.
Does that make sense?
Yeah.
Yeah, but, and as I said, this is going to give the level of improvement.
Mhm.
So if you can guarantee this outcome, then we are good to go. Right. So now go yeah. So now we know that there has to be a large number of people outside seeing a good number of fraction in both of A and B. But here we are trying, as we discussed, about this blowing up, H blow up business. We want to get a blow up, a proper blow up of the triangle, right? What we really wanted was something like this. It's not just two vertex subsets, but 3 disjoint vertex subsets, pairwise, very dense to each other, right? But this thing is not going to give us, already this outcome, because why? We only know that A and B are very dense to each other, but at the same time, we only know that each of the vertices here, only sees only at least epsilon, an epsilon fraction of each of A and B. So in particular, we cannot say immediately that this part is very dense to any of A and B, right? Meanwhile, what we wanted to get is a proper blow up of the triangle, a near proper blow up of a near blow up of the triangle, where pairs are pairwise dense to each other. So there has to be something, some result that could actually turn this weakly dense condition to a properly dense one. And that's actually contained with the next result. But the lemma, which is important behind proof. So it's going to be way to suddenly turn this sort of a low density outcome into very high density outcome. So lemma. So here again we have a graph H. Now for simplicity, let me preset the numbers of A, B, and C. Now we have the graph G. With this drawing vertex set, let me say A and B. This drawing, and such that every vertex in A is maybe using A and B because I keep using A and B for pair sets and X and Y. X and Y, this drawing vertex sets of G such that every vertex in X is adjacent to at least epsilon times Y. Rho is using 1. Right, so far, I mean, this is just a condition, saying that X and Y cannot be sparse to each other. The density will still be pretty low, okay, especially when epsilon is small. So again, here epsilon is 0.5. Then one follows. So first of all, so here's H, and I think I will need one more vertex in H. Let me say G is a vertex in H. So either the number of copies of H minus G in some subset of Y is going to be low. So the number of let me say Y prime is the most recommendations. So again, setting here is you only have two numbers. So either when this is utmost epsilon less than epsilon to the b times Y prime raised to the power of H minus 1. So you have a very low count in some subset of Y, in some decent subset of Y, where the prime Y prime is this epsilon. So this is actually a local condition. We are trying to restrict the count of some induced graph of H into a possibly small subset of Y. That's the first condition. The second condition is going to be the second outcome. It's going to be the number of copies of H now in G, but actually not exactly in G. I mean, that doesn't have to be in G, but actually some sort of spanning copy of H between X and Y. But let me just say the number of copies of H in G is going to be at least epsilon raised to the power of H times A plus B. That becomes B plus A in the ocean level. B raised to the power of H. This actually the outcome is similar to the second outcome. I mean, we have lots of copies of H and G. And the third outcome is the density increment outcome. It says we can actually string each of X and Y by a decent factor such that the resulting pair is very dense to each other. So it exists. X prime, subset of X, Y prime, subset of Y, with X prime, at least epsilon, acting to the same power. Such that X prime is epsilon raised to the power of A tends to 5 prime. So the picture is going to be X and Y. And the final outcome says two subsets, X prime, Y prime, very densely charged. What conditions for what? Oh, yeah, I see. For some. Okay, so let me say for some. Thank you. Actually, it is not hard to guess. I mean, this Y prime is going to be the neighborhood of some vertex X and Y. Yeah. Any other question?
How can this lemma apply to this picture?
Yeah, so that's what I'm gonna explain next.
Okay.
I'm not really going to the proof right away. Check here in the statement of the lemma, then the any question? Or as well. So for a moment, just forget about these exponents. I mean, there are some constants, but they'll actually work out later. Okay, so now going back to this picture. So we have a pretty good subset of vertices, right? I mean, the size is pretty big, it's linear in the number of vertices of the whole strategy, and each of them, so each of the vertices here sees a decent number of people in each of A and B. Now let me try to turn this into a proper triangle blow up like this. Okay. So I mean, of course, I mean here we are doing up to some outcome. So we have to allow some exception here. But I mean that exception is going to be just technical, and then we can resolve that later. So first, let me say this is C.
There is one question from
Yeah.
Maybe it's regarding the statement of the lemma.
Yeah.
Is there any size condition on X and Y?
No, there's no. I mean, so in practice, I think X and Y are going to be at least poly epsilon times G. But I think this lemma has nothing to do with the size of X and Y. So it's pretty general. Any other question? Right. So now let me say this is A, B, C, D, E. This is E. Right. So now we know that every vertex in E, right, you see at least an epsilon fraction of the vertices in A, which is exactly the condition for X and Y here in the lemma. Right. So now up to some exception, if I apply this lemma, then there's going to be three outcomes. Right. So either that means some subset of A which is actually some neighborhood of some vertex. It means which is actually the neighborhood of some vertex here has to contain very few copies of H minus G. So maybe either. So now we have three outcomes either. Has to be utmost some power epsilon. Prime raised to the power of H. But that's going to be the first outcome. Second outcome is I can conclude immediately that there has to be lots of copies of H and G, which is a win. Because we are in the H-free subgraph G, right? Or I can string E and A into two subsets very dense to each other. So string and A prime is epsilon raised to some power. So E prime is epsilon b raised to some power, big power B. Say A prime. Yeah. So the gist here is if we are doing some sort of induction on the number of vertices of H, then the first outcome is actually going to be a good outcome, right? Because we can restrict to an induced subgraph. We can zoom in an induced subgraph of G with very few copies of H minus G. And imagine we try to prove this main result, this main loglog improvement also by induction on H, then presumably this is going to be a good outcome. That's the first thing. The second thing is this second outcome cannot hold in any H-free graph G. And the reason here is because the number of copies of H in G has to be 0. So the only possible outcome that can hold, which can probably trouble us, is the third outcome, which we can turn A and E to a very dense pair. So now we try to move this. So here is a subset of E. This is E prime, and this is a quotient A, which is A prime. Now let me say A prime exercise at least some power of epsilon constant. Now they are very dense to each other. So in some sense, I'm halfway to this configuration. This upper hash has turned this upper pair, right, has turned into a dense pair. So what about the relation between this subset A prime and this B? If I can reset the density between A and B at the beginning to be very low, so if the density parameter between A and B at the beginning is something much smaller than the shrinkage factor of A prime versus A, then I'm still good, right? But I can still say that A prime is still very dense to B. Does that make sense? And I can totally arrange A to be very sparse to B at the beginning, and so that the shrinkage factor of A prime versus A is going to be much bigger than the density parameter between A and B. Okay, so this is a bit abstract, and hopefully in the notes will explain this a little bit more. But so this A prime. This is A prime. I mean, this is E prime. So what about E prime versus B? Again, I mean, everyone in E prime, we still sees a decent fraction of B, right? Because E prime is just a subset of E, which is, I mean, which you already have from definition. And now I can apply lemma again. Now try to shrink E prime a little bit more into E double prime. And still by some power of epsilon. This B is going to be shrunken into another subset B prime, which is of size also this only epsilon times B. And now we have E prime, sorry, E double prime and B prime are very dense to each other. And by the same reasoning as before, if I try to preset the density parameter between A and B to be very low at the beginning, be very small, then I can still guarantee that A prime and B prime at the end are still very dense to each other. So now I have completed this second pair, which is actually this outcome. A near blow up of the triangle. So the final picture is going to be A prime, B prime, and E double prime. Does that make sense? Any question?
So when you get this and finally what we will do when I mean when you get this and what we will do finally to get this form.
Yeah, I will go into that later because I mean this is like a sequence of steps and try to explain the idea behind it. And hopefully it will clarify the proof a little bit. But I mean this is just a sequence of ideas behind. I think we have the rest 40 or 45 minutes and try to explain that more. Yeah. So actually, I mean, the proof of this is going to occupy the whole talk today. Any other question about this deduction? If not, then I think maybe we have 5 minutes break.
Okay, so we restart.
So, okay, so with the break, there was some questions about this flow up. Right? So so far, I mean, we already discussed how to get a near block of a triangle. But what about a more complex configuration? So let me try to explain a bit more. A good example might be the 4 vertex 5 people. Okay. So P4. So let me try to assume at some point. Again, we start from a very dense pair. We start with a very dense pair. Again, A is B. Now the copy of P4 that I'm trying to aim for is like this. So this is supposed to be so let's A, B, and C, and G. Okay. So I already have completed this SGAED. Right. And again, now look at the rest of the world and see how it attaches to this pair. So now, the step is going to be very similar to the triangle business. If a linear number of vertices outside are very dense to A, then I can get the second outcome in the conjecture of a Poisson circle. That's actually a polynomial versus linear dense A. So I may assume that this quotient, these are the vertices, very dense to A. It's very few, so few vertices very dense to A. And how few? At most, let me say 1 in 10 for the rest of the world. And at the same time, I also look at those very sparse to be just like in the triangle business. Right? And again, I can deduce that at most 1/10 of the number of vertices G are very sparse to be, so at most. Okay, so what this means is, maybe more than, much more than 1/2 the rest of the world are at the same time seeing addition quotient of B and unseeing the addition quotient of B. Right, so the rest here is supposed to be huge, more than, so yeah, so the relative area of the boxes and not quite correct. So at least this many vertices of G are these three needs to be sparse to A, and these are the dense. By this I mean everybody here has at least epsilon. I mean, at least epsilon times B neighbors in B, and has at least epsilon times B neighbors in A. Oh, sorry, non-neighbors in A. So now I do the lemma again, and the lemma says either the count of H and G is already large, or I can string one of A and B by a poly epsilon factor to an induced subgraph with very small number of copies H minus G, I mean H minus small g, or I can string this big side here again by some power of epsilon. I can string it by some power of epsilon factor, such that now at the same time I can string A and I can string B, A prime and B prime, such that this big circle here, let me say E prime, for example, E prime is very sparse to A prime, and E prime is very dense to B. And at the same time, I can still arrange that A prime is very dense to B prime, just as similar as in the triangle business. So what this brings is, it's going to be this A prime, this B prime. I must say E prime, maybe C prime. It's better. So C prime. Now I have completed GA, PH, GB, GBGC, and the non-H GAGC in B4. Right. I have completed the first three vertices. So now I do it again. Or if I want to build a block corresponding to GD, and I want to construct the non-edges JGD, GBGD, and the H GCGD. And the idea here is you can look at those very dense to A very dense to be prime, look at those very dense to be prime, and look at those very sparse to C prime. And again, I may assume that all of these three vertex subsets have to be at most some small linear factor of the number of vertices of the host property. Now, which means that a huge chunk of the rest of the world are at the same time decently sparse to A prime, decently sparse to B prime, and decently dense to C prime. And now it suffices to apply the lemma one more time in string A prime, B prime, and C prime, just a little bit more by some power epsilon, or yeah, by some power epsilon, and also string this big chunk also by some power epsilon to get the final blowout. So this will become, we say this is D double prime, for example, and then subset C double prime, V double prime, V double prime. So now I've completed the near blowout of this for vertex path. Okay, so that's how you're going to handle, I mean, edges and the non-edges. Right. Yeah, so far so good, and there are actually some issues that I will try to clarify later. But for the moment, just look at this lemma. I think I try to explain the idea behind the proof. But any question? Right. So how to prove this lemma? So as I said, I mean, let's just forget about the exponents epsilon. I mean, they're all some power epsilon, and you can choose them, I mean, suitably if you understand the idea of the proof. Now look at two sides x and y in the graph. So my plan is to say that the first outcome and the third outcome cannot hold. And my goal is to try to build lots and lots of copies of each G. Okay. So what does it mean that the first outcome doesn't hold? If I pick an arbitrary vertex in X, I think there's an issue. Oh, I see. That's a bit. Now I understand the question. So I think this should be X times Y to the ratio of power minus 1. Sorry. Yeah, but so just to make all of them independent of G, and this lemma only concerns X and Y. Otherwise, we need to have some conditions on X and Y. Okay. Okay, so now going back to this picture. I pick a protection X, and I know that the first outcome cannot hold. Now look at this neighbor Y. Let me call this vertex X. So now look at the neighbors of X in Y. How many vertices are there? By definition, this number is at least epsilon times Y. Right? At least epsilon times Y neighbors of X on the right hand side. And now the first outcome doesn't hold, which means there has to be a large number of copies of H minus G inside this neighborhood. Right? So H minus G is here. And there are many of them. many of them. Okay. So what this means is, now here's the picture. G, this is H minus G, right? This is, I mean, this lower part is the set of neighbors of G and H. This upper part is set of non-neighbors of G and H. But so far, what we have got is a copy, I mean, many copies of H minus G together with some vertex complete to all of them. Right? So the picture currently is like G, and here is a copy of H minus G, and with this vertex complete to all of them. And how many copies of this configuration are there in this picture? So the number of such copy, I mean, so now let me say, we copy and split. So we copy split if the image of this vertex G is in X, and the image of H minus G is in Y. So how many split copies are there? So the number of split copies of so now the graph is going to be G. I mean, use equal notation, G complete to H, which is this graph. This can be at least X times epsilon with some power, right? To the B times Y prime H minus 1. But I know that a Y prime, which is this neighborhood, has at least epsilon times Y. So it's going to be at least X times epsilon to the B epsilon Y raised to the power of H minus 1, which is epsilon to the B plus H minus 1 times X times Y raised to the power of H minus 1. Okay, so now, so for this moment, I mean, the shape of the lower bound is already very similar to the shape of the lower bound in the second option, right? But that is about, I mean, the lower bound of the number of split copies of G compared to H minus G in this picture. So now, what am I going to do? What I'm going to do is to try to emulate the sort of business as in the lemma above. We try to, so now here, so now instead of adding edges one at a time, what I'm going to do is to try to remove each edge one at a time to get from this graph to the original copy of each. Okay. So what am I going to do now is to enumerate the neighbors and I think the non-neighbors, the non-neighbors of G in H minus G first. And let me say they are W1, W2 to W3. So here are the non-neighbors. Here are the non-neighbors of G in H. Now I'm going to fix a copy. I mean, I'm going to fix a split copy of this graph, or in other words, I'm going to fix a copy of H minus G minus W1 in Y. And I'm going to look at the set of candidates for W1. So this is the set of candidates for W1. And at the same time, instead of looking at just one vertex, I'm going to look at the set of candidates for G. So now we have two sets. Right? The point here is, I mean, as we know from this count, right? I mean, if we're trying to do something similar to what we did with the lemma above yesterday, then we know that there has to be actually many copies of H minus G minus H minus W1 inside Y, which can be extended in many ways to a full copy of this G compared to H minus G in this picture, right? So, which means there has to be a copy here such that there are many, I mean, there are a good number of edges going between the two sets of candidates, one for G and one for W1. Is that good? So, which means this set of candidates for G has to be a decent portion of X. And at the same time, this set of candidates for Y has to be a decent, sorry, this set of candidates for W1 has to be of a decent portion of Y. Right? Because there are a good number of edges here. So I'm not going to do numbers, but right here. So number of candidates for G is going to get this for epsilon times X. Number of candidates for W1 is to be getting this for epsilon times Y. Okay. So now, under the assumption that this third outcome cannot hold, I should have that there has to be a good number of missing edges between these two candidate sets. Otherwise, they're going to be very against each other. Right? So now I'm trying to erase this. Let's say number of missing edges. So from left to right, these two sets have to be, it has to be not too small. And if I try to repeat this sort of thing for all of the good copies of H minus G minus W1 living inside Y, I'm gonna have succeeded in removing the H G W1 in this graph. So now the next graph that I have is going to be G now the W1, and G is adjacent to all vertices here except for W1. So what I can infer from this picture is number of split copies of G complete to H minus G altogether minus GW1 has to be at least again for epsilon times X times Y raised to the power of H minus 1. Okay, so now you probably have seen some pattern here, right? Now I keep repeating this argument, not only for W1, also for W2 to WK. We keep removing the edges, I mean GWI from this picture until I get a proper copy of H. I mean, actually, a proper split copy of H between X and Y. And actually, many copies of H between X and Y. So that's the idea. And then all what's left to do is try to fill in the numbers with the exponents and try to make it work. Any question?
I think the first condition should be for every Y prime.
No, for some Y prime.
But
Because if it, I mean, if that doesn't hold, then for every Y prime of size, at least epsilon times Y, the count of h minus g in one time is going to be many.
Oh, okay.
Good?
Yeah.
So this thing is a bit no question? Good. So I hope this is this clarifies somewhat the idea behind. Perhaps the most important part of the proof of this log improvement. But now, there are some small technical issues, non-numbers that we have to deal with. But is everyone happy with the lemma and the proof idea? So, okay, so I have 20 minutes and trying to explain the problems now. So. Right now. Yeah, so now look at the lemma. Yeah, so as we discussed, there are three outcomes, and we have assumed that the first outcome is presumably good, in the sense that if we are trying to prove some statement by induction of the number of vertices of H, then this should be a good outcome for us, so that we can apply induction. But there's an issue here. First of all, is the use of this outcome in the conjecture. We try. So what we have done so far is to try to aim for this outcome. We try to say at some point, there has to be a very sparse or very dense pair of polynomial size versus linear. And now imagine if you're trying to do induction on the number of vertices of H, then it seems like this outcome is not good for us. And the reason here is because this subset Y prime is only an epsilon fraction Y. And meanwhile, in this conjecture, what we need to do, to get this outcome is a subset which is properly linear in the number of vertices of G. So long story short, this Y prime could be too small for us to apply this outcome if you're trying to do induction. So in order to resolve this issue, let us try to understand why this conjecture is going to imply the log improvement. So what we have here is, in an H-free host graph G, we have two subsets disjoint. Two subsets disjoint to each other, such that the large part is very dense or very sparse to the small part, and the large part is of size about linear in G. So what we usually do in the context of induced graphs is try to iterate this outcome inside the big part. So what am I going to have if I try to repeat the sparse or dense linear pair inside the big part? Again, there's going to be a small subset of polynomial vector. So now versus a linear function of the big part. So if this was originally G over D, then this part is going to have size G over D squared. Right, and this is going to be poly epsilon times G over D, which is still roughly poly epsilon times G. So now, in particular, we have obtained three sets, 1, 2, 3, such that this is very sparse or very dense to this top set, and both of these are very sparse or very dense at the same time to this left-hand side set. Okay. So what if I keep repeating the lemma? I keep iterating the lemma inside the big parts until I cannot do it anymore. So here, every time I apply the not the lemma, but the outcome over there. Every time I apply the outcome, the polynomial versus linear outcome, the exponent of D is going to increase by 1. Right? It's going to increase by 1. So after case step, after case steps, what am I going to have is a series, a sequence of disjoint subsets. The first k minus 1 of them are small. The first k of them are small. So the first k blocks, let me say k blocks, size poly epsilon or G, and the last block is going to be the size at least G over D to the k. Right? So it's going to look like this. And with the property that for every block, if I choose any block from this sequence, then all of the blocks on this right-hand side are going to have the same kind of adjacency, in a sense of dense or sparse towards itself. So if you want, no, let me see, you want 2, 3, so what is VK? This is VK plus 1. If you pick an arbitrary BI from the sequence, then every block BJ, all of the blocks BJ to the right-hand side of it are going to have the same kind of density towards BI, right? Okay. So now, of course, I cannot apply the outcome, or I cannot iterate the linear versus polynomial outcome for too many times, because if I do so, then I might risk shrinking this larger set by too much. Then it's going to become very small and also going to be useless. So an ideal way to choose the number k is to choose it so that this number d to the k will become some power of epsilon. So I want to choose k such that d to the k is a polynomial in epsilon. And ideally, k will become roughly log of 1 over epsilon. Okay. So long story short, the outcome in the Cohen-Psularkov conjecture has 2 vertex subsets, but this kind of asymmetric, right? This linear versus polynomial. But if we try to iterate this outcome for about log of 1 over epsilon times, then we're going to get a symmetric outcome. All of the blocks are, all of the subsets in the sequence are all of size poly epsilon times G, and they obey the same sort of uniform density condition. Does it make sense? I hope this explains a little bit. So now, the statement that we're really trying to aim for here is not going to be the Cohen-Psularkov conjecture. It's something else, which is exactly this. So let me try to write it down carefully. So theorem. For every H, there is here is one, such that for all H we graph P, and for all epsilon from 0 to 1/2. There are disjoint B1, B2, BK, BD, where K is, let me try to say, well, function of log 1 over x, sorry, 1 over epsilon. Such that BI is at least epsilon raised to the power of D times G for all I or 1 to K. And for I from 1 to K, the union of BI plus 1 to BK is epsilon half, or epsilon dense to BI. So first of all, as you can see, this is a pretty symmetric condition. I mean, up to this sort of density thing, which I will explain later. But at least in terms of the size, this is symmetric. We have a uniform bound, a uniform lower bound on the size of the BIs, which are of the form some power of epsilon times the number of the vertices of G. Right? And if you're trying to prove this statement by induction on the number of vertices of H, then this outcome, then this first outcome in the tripartite lemma here is going to be a good thing, because everything is going to be absorbed into some power epsilon. Okay. And the next thing here is this going to imply the loglog improvement? And the answer is yes, because of this number. Yeah, so if you compare this to the Erdős-Hajnal theorem there, then this is a significant improvement, because the Erdős-Hajnal theorem only gives you 2 sets, but this gives you about log of 1 over epsilon sets. And in fact, I mean, if you try to do some numbers, I mean, try to mimic the way we derive from the Erdős-Hajnal theorem. I mean, we derive the Erdős-Hajnal bound from the Erdős-Hajnal theorem by putting epsilon to be 1 over mu G or something like that. Then, in fact, if you can prove this theorem for any H, with K being any function of epsilon, then the bound is going to be of the shape 2 to the C root log n. So K here is K of epsilon. So log of K n over n. But this actually what the trick of putting epsilon to be mu G inverse would give. So here in this theorem, we know that K of epsilon is roughly log of 1 over epsilon. So if you put this function in, then this is going to be exactly log n. Okay. And you can do it by doing some calculation. I mean, it's going to be messy, and I'm not going to do it here. Okay. Yeah, so this is the theorem that that is supposed that is supposed to be proved during the course of the proof of this learning. And everything about, I mean, everything is about the proof, I mean, trying to get a polynomial versus linear pair, I mean, very sparse or very dense pair can all be turned into this outcome, which is uniform. Okay. So I have one last comment about, I mean, the second outcome here. So there is a concept in graph theory called threshold graphs, which can be defined as follows. The threshold graphs. So the H is threshold. If for every induced graph F H, the real vertex be F such that V is complete to Bf minus V or anti-complete. So in other words, I mean, every threshold graph can be used by, you start with one vertex and then you add a new vertex adjacent or not adjacent to it. And then you add a new vertex adjacent to both of these two vertices or non-adjacent to both of them. And you keep going. So it could look like this. So every time you add a new vertex, it has to be uniformly adjacent or uniformly not adjacent to all of the previous vertices. So this is the threshold graph. And the observation here is every threshold graph is a co-graph. The observation. Yeah, so every threshold graph is a co-graph. So they're going to contain a clique or independent set of size is about root of a number of vertices. So why do I talk about threshold graphs? Because if you look at the pattern of the blocks we want to be K in this theorem, then the pattern graph of this, I mean of these blocks is going to resemble a threshold graph. And so you can extract from this outcome, from this theorem, a uniformly dense or uniformly sparse sequence of blocks. So the L such that the J epsilon sparse or epsilon dense to be I for all I less than J. And also L is at least about roughly root of one of epsilon. So yeah, so and again, if you plug this function L epsilon into this bound, then you can also recover the log result. So that's all. Thank you. That's it for today.